a body, which we'll discuss later. Yeah. Now this force, all the forces that we find in nature around us, we have classified them in different types, different categories. One category was like fundamental forces: gravitational, electromagnetic, weak nuclear, and strong nuclear. Then another category is contact and non-contact forces. I think I was telling you, forces which can act between two bodies without the need of physical contact between the bodies. We call them as non-contact forces. And forces which can act only due to physical contact, like pulling, pushing, friction, air resistance, uh, tension in strings, all these things, they are contact forces. Okay. Then another, you can say, category of forces, we call them as common forces in mechanics. Common forces in mechanics, which we will discuss today. So common forces in mechanics means the forces that we come across in our day-to-day life. What are these forces? See, common forces in mechanics. Okay.
So contact and non-contact.
I told gravity, magnetic force are non-contact forces, friction, air resistance, tension, these are contact forces. That it's self-explanatory. Right. Common forces in mechanics. What are the common forces? First, weight. First force is weight. And try to understand these forces very, very clearly. All you study is applications of these forces. That's all. When you go to class 11, you study the applications in different situations of these common forces that you are studying here. Okay, weight is the first force. How do we define this weight actually? We know this is, let us say, Earth, and this is a body of mass, let us say small m, which is present on the surface of Earth. And we know Earth has a gravitational force. Earth can exert gravitational force on other bodies. So Earth is pulling this body of mass small m towards it. Earth is pulling this body towards, let us say this is you. You are standing here on the surface of Earth. So Earth is pulling you towards its center due to gravitational force. Okay. So if Earth is pulling you, or Earth is pulling any body towards it, that means there is force. Gravity is a force. And from Newton's second law, we have already studied wherever there is the acceleration. Wherever there is force, there will be acceleration. So on you, this, let us say your mass is m. On you of mass m, this gravitational force is acting. So definitely acceleration will be produced. Acceleration will be produced. And we have named that acceleration, which is produced by gravitational force, as acceleration due to gravity. As acceleration due to gravity, small g, which I already used in our earlier chapters. So from F equal to ma, Newton's second law, mass is mass, same thing. Acceleration produced due to gravitational force, we call it as acceleration due to gravity. So I'm replacing this a with g. So this is the gravitational force acting on you. F equal to mg is the gravitational force acting on you. And it is this gravitational force acting on you which you feel as your weight. Weight of a body is nothing but the gravitational force acting on that body. So it is the gravitational force acting on a body.
Sir, I have a doubt.
Hmm.
Sir, that means that we have gravity, no, sir.
Hmm.
That means every object which has mass, like exerts gravity, no, sir.
Yes.
That means in space also between two astronauts, there will be gravitation.
Yes. There will be.
Then why don't they like stick together, sir, in the
If
space?
there is no other body around them, near them, for a very very far away distance, then they will stick together. If two astronauts are floating in space, if two astronauts are floating in space, let us say this is Earth or Moon or something, this Earth or Moon will be exerting gravitational force on both of this. It's not like gravitational force will be zero in space. It's not zero. Practically, it's not zero, because once you study gravitation, you will understand that the gravitational force between two bodies is given by the formula F equal to gm1 m2 by r square, where r is distance between the two bodies. Or in if you take between Earth and astronaut, this is r. R is gravitational force will become zero only when r becomes infinity. So if an astronaut is floating in space, it's not like gravitational force on him is zero. Gravitational force is there on him due to Earth, due to Moon, due to Jupiter, due to Sun. All these things, they are exerting gravitational force on that astronaut. So, due to all these forces, as their magnitude will be much larger than the gravitational force between these two astronauts, they will not stick together. If you imagine a situation where there is nothing near them, they are very far away in space, let us say at a distance of infinity, then if you leave them like that, they will slowly come close and stick together.
Sir,
Yes,
sir, what is a capital G here?
that is different.
Gravity force in
Capital
newtons.
G is a different thing. It is a constant of proportionality that you get there. We'll come across that when we study gravitation chapter.
Sir, what is R, sir?
In India, sir.
Don't go into the details of that formula. To understand that formula, you need to understand some other things, which is not a part of this chapter. So my point was gravitational force depends on distance between the bodies. Greater the distance, lesser the force. For gravitational force to become zero, R should become infinity. Distance between the two bodies should become infinity. And that is a ideal situation, hypothetical situation. Okay, so we have defined weight as the gravitational force acting on a body. What is weight essentially? Weight is force.
Sir, R is the distance, sir.
Distance between two bodies.
Okay.
So weight is a force. Weight is a force. And okay, and you should understand what is the difference between mass and weight. This is very important. What is the difference between mass and weight? Mass is,
Sir, can I?
it is the quantity of matter contained in a body. Quantity of matter means you can understand it like, suppose I have a pen. I have a pen. This pen is made of matter. Matter is made of molecules. Molecules are made of atoms. So ultimately, this pen is made of atoms. Let us say in this pen there are some 100 number of atoms. 100 number of atoms. Okay. Then I have a say a textbook. Book is larger than a pen, obviously, and this book, let us say, it is made up of 1,000 number of atoms. So if you consider the quantity of matter present in a pen, it is less than the quantity of matter present in a book. We represent this quantity of matter present in a body or contained in a body as its mass. Greater the quantity of matter, greater the mass. Lesser the quantity of matter, lesser the mass. Okay. Don't think that mass represents size. Size has got nothing to do with mass. It's a different thing. Mass depends only on the quantity of matter contained in a body, and it is measured in unit of mass. It is measured in kg. Standard SI unit is kg, kilogram. Wherever you purchase any goods or groceries, you will be measuring mostly in kilograms. Okay, and it is a scalar quantity. Mass is a scalar quantity. It does not depend on direction, or it does not have any particular direction. Then another point, it is independent of position. Mass of a body is independent of position. What does this mean? Suppose take that example of that pen. In that pen, we have 100 atoms. Okay.
Sir, in everywhere in the universe, it has 100 atoms only.
Or let us say I have a body whose mass is some 1 kg. Its mass is 1 kg. It has some 100,000, 10,000, 1 million, some number of atoms in it. Okay. This body is on the surface of Earth. Its mass is 1 kg. If I take this body to moon, its mass will be 1 kg, because if I take it from here to moon, the number of atoms in it will not change. 1,000 atoms will not become 1,001, or they will not become 999. 1,000 will be the same 1,000 number. So its mass will be same 1 kg on moon also. If I take it to Jupiter, its mass is 1 kg. Number of atoms is not changing. If I take it anywhere in the universe, its mass will be same. That's why mass of a body is independent of its position. Does not depend on where the body is placed. It is always the same, unless you break down that body. Mass does not change. Okay. Mass. This is mass. Then what is weight? As I told you, the definition of it is the gravitational force acting on a body. It is the gravitational force acting on a body. So weight is entirely different from mass. Try to understand this. Weight is a force. Mass is quantity of matter. They are completely different from each other. And as weight is a force, you cannot measure force in kg. Force is measured in Newton. SI unit is Newton. And force is a vector quantity. So weight is a vector quantity. And weight of a body, it depends on position of the body. It depends on position of the body. How? Because
So the weight of an object is 1/6 on the moon compared to its.
Because as I was telling in this example, if you place a body of mass m on the surface of Earth, this is a body of mass m on the surface of Earth. Gravitational force is acting on it. Gravitational force is acting on it. Force is ma. And as it is gravitational force, acceleration produced will be acceleration due to gravity. Mg. What is this force acting? Gravitational force acting on the body. and we call this acceleration, this force, as weight. Therefore, weight of a body is mg. Weight of a body is mg. This is a very important point. If mass of a body is m, then its weight is mg. We will use this at least 100 times in the coming topics. So if mass of a body is m, its weight will be mg. Its weight will be mg. Mass multiplied by acceleration due to gravity. If and this acceleration due to gravity, its standard value is 9.8 meter per second square, but not always, but not everywhere. On the surface of Earth, g is 9.8. In the chapter called gravitation, you will study that g is not constant; it changes with respect to position of the ball. If you go above the surface, g decreases. If you go below the surface of Earth into the Earth, g decreases. So, and g depends on the dimension of the planet also. For Earth, value of g is 9.8. For Moon, it is
1.61, sir.
1.6. For Jupiter, it is some 13 times that of Earth, and for on Mars, it is almost some 75% of that of Earth. So g, value of g, changes from planet to planet, and even on the same planet, it changes from position to position. So g is not constant. If g is not constant, weight is also not constant. Depends on position. So if let us say a
Sir,
yes,
sir, we can say that mass is the weight with the irrespective of the gravity, no, sir.
mass is not weight.
Irrespective of gravity, sir.
No, mass is not weight. You cannot describe mass in terms of weight.
Okay, sir.
Don't make it like m is equal to w by g. This is mathematically okay, but physically it's not the definition of weight. Suppose weight of a person has, let us say, his mass is on Earth some 60 kg. 60 kg. Then what is his weight? mg, which is 60 into, I am taking g as 10, round figure, which is
100 kg, sir.
600 Newton. So don't say kg, we are describing weight. You use kg to measure mass. Weight is not mass, weight is a force, so it must be represented, it must be measured in Newton. Weight is a force. You first remove from your mind this. See, this problem is because suppose if I ask you, what is your weight? Anyone who will say? Anyone? What is your weight?
Sir, 44
44 what?
kg units.
44 kg. So 44 kg. Is this weight or mass?
It is not, sir.
Mass, sir.
Sir,
As you are expressing it in kg, definitely it should be mass. It is not weight. This is a general, what you call it, mistake that we make regularly every day. We measure our mass, we measure our mass, but call it weight. When you stand on a weighing machine, the reading that it shows, it is your mass or weight.
Mass, sir.
The reading it shows is your mass because it is showing in kg. Because it's showing it in kg, it should be mass. But in reality, that weighing machine measures your weight, not mass. That weighing machine measures your weight. Measures weight but shows mass. How is this possible?
Sir, it measures, it has weight units, but because of the gravity, it shows us the mass unit.
See, it is like this. Let us say this is your scale of weighing machine. This is 0, 20, 40, 60, 80, 100, 120, something like this. Okay. In reality, when you stand on the weighing machine, your weight, that means the gravitational force with which Earth is pulling you, that acts on the weighing machine. So, force is acting on the weighing machine. So, if let us say your mass is some 60 kg, then your weight is
600 newtons, sir.
600 Newton. So that needle or the pointer of the weighing machine, it is pointing here. In reality, this is not 60, but it is 600. Is 600. But if you tell to a common man that your weight is 600 Newton or 540 Newton or 700 Newton, they will not understand, because all
Yes,
of
sir.
us, even an illiterate person, if you go to market to purchase vegetables, he or she, the vegetable vendor, he or she will be very well versed with kilograms. If you go and ask them for 1 Newton of tomatoes, they will not understand what you are asking. So kg is a unit which has become very popular. That's why this weight, which is measured in Newton, is converted into mass. How? Dividing by g.
Dividing by 10, sir.
G. So this 600, in reality, it will be measured in 600, but this 0 is removed because I am dividing it by 10. Wrong figure. G is 10. So 600 becomes 60. If a person has, let us say, 800 Newton weight, then the pointer will be pointing here on 800 Newton. But this 0 is removed on the scale and it's written only as 80. So in reality, it is 800 Newton, but for our convenience, so that everyone can understand easily, it is converted into mass and shown as 80 kg. Okay. So what is wrong here? In someone said his weight is 44 kg. What is wrong here? There are two things wrong. Either you should call this weight as mass, or you should change this unit to Newton. If you change this unit to Newton, this becomes 440.
440 newtons.
So in reality, this is not your weight, this is your mass. 44 kg is your mass. Remember, blind thumb rule. If it is in kg, it is mass. If it is weight, it should be Newton. That's all. Nothing complicated here. If it is in kg, it is mass. That's all. To convert mass into weight, what should you do? You should multiply it by g. If you multiply mass by g, acceleration due to gravity, you will get weight. Okay, I was telling you this example. The weight of a person, the mass of a person on the surface of Earth is 60 kg. So his weight on the surface of Earth is 60 into 10, 600 Newton. 600 Newton. Okay. The same person. Now he is on moon. If you take the 60 kg person to moon, will he become 50 kg or 70 kg?
Sir, it will be like that only, sir, because
His
mass
mass
is independent of
will be
position.
60 kg. Mass does not change. But his weight on the surface of moon will be m. Mass is same. G. Which G? G on moon. Here this is G on Earth. And I think while telling you this kinematics, I told you acceleration due to gravity on moon is 1/6 of that of Earth. 1/6 of that of Earth. So this acceleration due to gravity on moon is acceleration due to gravity on Earth by 6. So his mass is 60 into acceleration due to gravity Earth is 10 divided by 60. 6 1 6 tenths. How much is it? 100 Newton. On Earth he weighed 600 Newton. On moon he will weigh only 100 Newton. What is changing? Weight is changing.
Same,
But is
sir.
his mass changing? No. Mass does not depend on position. Weight depends on position.
Sir, in the equation after mg, what did you write, sir?
After
mg, sir. Down.
G on Earth.
Okay.
100 Newton. So this is the difference between mass and weight. This is the difference between mass and weight. If you want to, if you are given mass of a body